1/2. How else could you look at that function, Jack?
Square root of x.
Yeah, that's equal to the square root of x. And Jack, when you have square roots, what has to happen with square roots?
You take the whatever's inside the square root
And set it equal to 0. What else besides equal to 0, Jack? Besides equal to, what kind of numbers can't you take the square root of? Negative numbers. So it has to be greater than or equal to 0. So whatever's underneath the square root, in this case it's just x, x must be greater than or equal to 0. If there was another expression underneath there, then we would say that whole expression has to be greater than or equal to 0. So Jack, in interval notation, if x must be greater than or equal to 0, how would you write that?
0,
And then what goes around the 0?
bracket,
Perfect. Bracket in a parenthesis. So whatever's underneath the radical must be greater than or equal to 0. It's allowed to be 0 because the square root of 0 is just 0. But the square root of -1 doesn't work. So that's why it has to be greater than or equal to 0. The next one, now it's the same function. The exponent of 1/2 is the same thing as the square root of x. So that's going to be from 0 to infinity. And again, bracket with the 0. Infinity is a parenthesis because we don't have an actual number to assign to that. So then if we use the same concept that we did for 1 and 2, whatever is underneath the radical, you're taking that little expression and saying that has to be greater than or equal to 0. So JT, that means x must be greater than or equal to -3. So if you solve that little expression for x, then that tells you the smallest number that x can be. Because if I put a -3 in here, -3 plus 3 is 0. And again, we can take the square root of 0. But if I use a -4, -4 plus 3 is -1. And that cannot work. So JT, if our inequality says x is greater than or equal to -3, how would you write that as an interval? Yeah, and what goes along or around the -3? A bracket, because it's allowed to be -3, and then a parenthesis. So this interval says your graph starts at -3 and it stretches all the way to infinity. That's what the interval is saying. So the way the graph is stretching from left to right. So number 4 is a little different because we have a negative exponent instead of a fractional exponent. Chris, how would you write x to the -1? Yeah, we can write that as 1 over x. So it's the same thing as 1 over x. So the first 3 dealt with square roots. Chris, what do we have to think about when you have values in the denominator? Yeah. So if we think about it being equal to 0, then that's the number that cannot exist in the denominator because the denominator cannot be 0. So I cannot divide by 0. So in this case, it's just x, and it's not allowed to be 0. Whatever that number is that makes it 0, it can't be that value. I cannot take 1 divided by 0. It's undefined. Chris, how would you take that where x can't be 0 and write it as an interval? So 0 to infinity would be 1/2. If it cannot be a number, we put a parenthesis around it. If it's allowed to be a number, then we use a bracket. But there's another half to that. Right. So -infinity to 0, also in parentheses. It's both of them. So when we say it's not allowed to be 0, it's allowed to be everything less than 0, and that's what this part here says. The numbers less than 0, from -infinity up to 0. So that's the numbers on the left, the less than values. And then the numbers bigger than 0, from 0 to infinity.
Should 0 be
Should 0?
Should it be in a bar because it's the exact value?
It cannot be in a bar because if it would be, then you're saying it's allowed to be 0. And that means I'd be able to put a 0 down there. So that's why we put it in parentheses. So it's allowed to go right up until 0, but it's never allowed to be actually the number 0. Other questions? So the last one is also a fraction, and when you have fractions, you're only worried about the denominator. What makes the denominator 0? So Sadie, number 5, what makes the denominator 0? A 2. So if I solve the little expression in the denominator, x minus 2 equals 0, x is equal to 2. That's the number that makes the denominator 0. So it's not allowed to be that number. So whatever the value is in the denominator that makes it become 0, it can't be that value. So Sadie, how would you write that domain then? So again, you can't place a bracket there because a bracket means it's allowed to be that number, and it's not allowed to be that number. Those are the only 2 restrictions on domain. Any other function has a domain from negative infinity to positive infinity. So when you do domain, there's 2 things to think about. Is it a radical? Is it a fraction? Where's the x on the fraction? And where's the x in the denominator, or in the radical? So today we're going to use this, but we're going to try and combine functions together. And when we talk about combinations, there are 4 ways in math that you can do combinations that you would have learned very early on. Adding, subtracting, multiplying, and dividing. So those are 4 operations of math. And we're going to now perform those operations with algebra. So in your notes, it is section 6.3. So we're going to see if we can perform operations with functions, but also use the power functions, the rational functions that we've been working with, and the domain and range of those functions. So page 13 in your packet. So section 6.3, performing operations of functions, and then tomorrow we're going to do the second part where it says composition of functions. So no, we're not writing physical composition in English, but we're going to see what that means in math. So we've actually been working with rational expressions, rational exponents, pretty much all of chapter 6 since before Christmas. We've been working with exponents that have been fractions. So now we're going to look at those as functions instead of just expressions. So a function becomes an equation with a y and an x, and a power function has the form a, b to some kind of power. So I could say f of x is equal to 4x, maybe to the 3 halves. That's a power function, which is what we've been working with, except they have been expressions. So everything we've done has just been an x or maybe a y. It hasn't actually been a function. So a function, once you place the x and the y together into an equation form, then you have a function. So we've been working with these, we just have been working with them as expressions. So in the little chart below, there are 4 operations that we're going to try and apply to these functions. So now I have 2 functions. And it says we have f and g, so f of x and g of x. A new function h can be defined by performing any of the 4 basic functions. So that's just saying once I do an operation, add 2 equations together, I get a new equation. And we're going to call that h. So any new equation gets a new letter in function notation. So our 2 functions right here on the right side. One function is f of x equals 3x. The second function is g of x. So this is function notation that we talked about in chapter 2. So these are both functions. The first thing we're going to try and do is add them together to get a new function. So it says to add them, you're going to take f of x plus g of x. So in this case, literally, I'm going to take whatever represents f of x. So I'm going to add f of x, which is just 3x. I'm going to put my plus sign, to g of x, which is x plus 3. So here is my f of x function. Here is the g of x function. And literally, we're adding them together to create a new equation or a new function. So if you have 3x plus x plus 3, Chris, your new function would become, yeah. Say it again. Yeah, I thought you said 6 at first. I wanted to make sure. So add the like terms together, you get 4x plus 3. That's it. So because it's a new equation or a new function, we call that h of x. So if you look at the second one, it's subtraction. So we're going to do the same thing, except now we're going to subtract. So we have f of x minus g of x, same two functions. We're going to work with those same two. So f of x is 3x. God bless you. You're subtracting all of g of x. G of x was x plus 3. But that needs to go in parentheses because it's a quantity, and the whole quantity is being subtracted. You're not just subtracting the x of the function, you're subtracting the x plus 3, that whole part of the function. So, Michael, what would our new function h of x become when we combine the like terms together? Yeah, so that little negative sign is applied to the entire function, applied to both. So that becomes 2x, and now it's minus 3. So operations, adding and subtracting, the first two that you learned in kindergarten. And then in 3rd grade, you do multiplication and division. So now we're going to do multiplication and division with functions. So h of x, again, 3x. We're multiplying this with x plus 3. Because that second function is in quantity, we really put parentheses around that. And generally, we don't use the little multiplication sign because once you have parentheses, that means multiplication. So Nina, how would you multiply 3x times x plus 3?
Would you have to distribute 3x?
Yeah. What would that become?
3x squared plus 9x.
Good. And then the last one is division. So we take f of x, you divide it by g of x. Well, f of x is 3x. We're dividing that by g of x, which is x plus 3. And again, you have to kind of think about this as a quantity grouped together. So it's a whole group. Both of them are together. This expression cannot be simplified because 3x doesn't divide into both of them. So when you have something in the denominator, which you do to the first part of the denominator, you have to be able to do the second term. And if you can't divide by all of it, then we cannot divide at all. Questions? So this one you actually can't do anything to. It just stays like that. There's no way to simplify that or actually divide. Any questions? So underneath, we're going to talk about the domain of these problems. We were working with domain so that we can then start talking about domain with things. It says the domain of h. H is your new function. Consists of the x values that are in the domains of f of x and g of x. So the domain of our new function is kind of based off of the domain of the two separate functions, and we try and literally look at the domains and figure out where they overlap. Additionally, the domain of a quotient, meaning when we divide, does not include x values for which the denominator equals 0. Because if I have a fraction, the domain cannot be any numbers in the denominator of that fraction. Questions? So we're going to see if we can apply this to power functions or exponents. So we have two functions, two new functions at the top. F of x is 2x plus 7, g of x is 5x squared minus 6x plus 4. And it asks you to find the following. So we're finding f of x plus g of x, f of x minus g of x, and then we want to get the domain. So if we start off with f of x plus g of x, so literally, you're taking the equation or the expression that represents f of x, which is 2x plus 7. So that's f of x. You're adding that with all of the expression for g of x. Right here's g of x. Which we actually did when we were adding polynomials, except the polynomials were already set up for us. So now it's really just kind of using different notation. So Peter, if you add those together, what do you get?
5x squared minus 4x plus 2.
So my new function h of x is equal to 5x squared minus 4x plus 11. When you're combining those like terms, make sure you pull front the largest power. That's the standard form of writing a polynomial function. So the largest power goes first. We'll talk about the domain in a minute. Let's look at the next one. Or f of x minus g of x. So doing the same thing, using the same two functions except subtracting. So 2x plus 7 minus, because it's subtracting and you're subtracting a whole quantity, we have to subtract the 5x squared minus 6x plus 4. Subtraction is where the easiest mistake happens because you forget that you're subtracting all of the function, and a lot of people just want to subtract that first term. All of it gets subtracted. So Gavin, if you subtract that second function, our new function for h becomes
Negative 5x squared plus 9 plus 7.
Nice job. So again, that negative distributes to each one. So a negative 5x squared, a positive 6x, and a negative 4. Here.
It gets plus 8.
Plus what?
Plus 8.
Oh, sorry. My fault. Thank you. So then the last thing that we want to do is try and find the domain. So before using the answers, go back and look at the domain of the individual functions. So the domain is comprised or created from the domain of the individual functions. So the first function is f of x equals 2x plus 7. Chris, what kind of equation is that? What would the name of the function be? What's the graph of it look like? Yeah, it's linear. So this is a linear function. Chris, what's the domain of any linear function? Right. So the domain of a line is negative infinity to positive infinity. It has an odd power. The domain of any odd power function is negative infinity to positive infinity. So that's a line. Let's look at the second one. What type of function is 5x squared minus 6x plus 4? Josh. Yeah, that's a parabola. So x squared, this gives us a parabola. Josh, what's the domain of every parabola? Because a parabola is a U that stretches forever, further and further left and right. So its domain is negative infinity to positive infinity. So when you go down to do the domain of the operation, you're taking the domain of both and sometimes finding out where they overlap. Well, in this case, the domain is the same for each function, so that means the domain for the addition is negative infinity to positive infinity. And again, it's because the domain is the same for both f of x and g of x. If it was different, then I'd have to find the overlap. The domain of the subtraction is negative infinity to positive infinity. So it's a lot of the end. Questions? So there is another pair of functions underneath. And this pair now has exponents. So we have 4x to the 1/2, negative 9x to the 1/2. See if you can perform f of x plus g of x and f of x minus g of x. So Michael, the first function f of x plus g of x would be equal to?
Negative 5x.
Yeah, those are like terms. Combine the coefficients together that are in front. So you're adding 4 and negative 9. So like terms, they have the same variable and exponent. You combine the numbers in front. Michael, how about B?
13x.
So 13 and then x to the 1/2. All right, so then we have to decide what the domain is. We have 4x to the 1/2 and negative 9x to the 1/2. Jack, how can you write the x to the 1/2? What's that really saying? Yeah, this is really 4 square root of x, negative 9 square root of x. Jack, when you have a square root of x, what's the domain? So it has to have.
Negative infinity to, 0 to.
There you go. Remember, that has to be greater than or equal to 0. So 0 to infinity. Bracket, it's allowed to be 0 to infinity. Those are the two things when you have a radical or a fraction. We got to think about that. So 0 to infinity. So again, both of the domains are the same. So the domain would be 0 to infinity. So a radical must be greater than or equal to 0. All right, so there's yet one other pair underneath, and then I think there's a checkpoint at the bottom. So this one says we want to find f of x times g of x. And we have two different functions. One is a linear function, the other one has an exponent to it. So we want to take f of x times g of x. So 6x times x to the 3/4. So this now goes back to all the concepts that we've been working on. How would you simplify 6x times x to the 3/4? Peter?
You would add exponents of x.
Yeah. So we need to add the exponents. So when you're multiplying and you have the same basis, you add the exponents. So you have 1 plus 3/4. Peter, 1 is really, say it again? Yeah, so 1 plus 3/4, you're really taking 4/4 plus 3/4. So Peter, that exponent becomes,
6x.
right, 6x to the 7/4. So now you have to apply what we've learned to what we are learning now. So what we learned about combining exponents to the new stuff. So 6x to the 7/4. The next one, now we're dividing. So we have f of x divided by g of x. So that means we have 6x divided by x to the 3/4. I'm going to put a little 1 with that x. Dimitri, when you were dividing, what do you do with the exponents? You subtract. So the 1 is really 4/4 minus 3/4. And Dimitri, that becomes x to the, excellent, 1/4. Our new function is x to the 1/4. Sorry, there should be a little 6 in front. Don't forget the 6 that's sitting in front there. So you're subtracting the exponents. All right, the last thing we have to do is think about the domain. So the domain of a line, negative infinity to positive infinity. How would you write 3/4? How do you write that as a radical, Chris? Right. When you have an even radical, you cannot take the square root or the 4th root of a negative number. So whatever is underneath here has to be greater than or equal to 0. Because it's an even root, and I can't take the square root or the 4th root of a negative number. So that means the domain has to be 0 to infinity. So any radical When you go down here to do the domain, it's going to have to be from 0 to infinity, because right here. The next domain changes just slightly. There's a little change in the last domain. And it's a 0 with a parenthesis to infinity. And that's because the original problem started as a fraction. And when you have a fraction, you can't have a 0 in the denominator. So your homework is in the book today. It's 3 to 9, all of them 3 to 9. And then 48 to 53, all of them as well. And you're doing operations, adding, subtracting, multiplying, and dividing with functions. Anybody interested in doing 8 or 17 for tomorrow?
I'll do number 8.
You'll do number 8. Thanks, Sadie. You'll do 17, Alyssa? Awesome, thank you.